Good morning. My name is Mike Wamsley. I'm a global product manager in TE Connectivity. So I want to talk a little bit today about where the connector roadmap's going and how we're supporting changing architecture. So nobody really loves a connector because you throw them into the system, they add signal loss, noise, they take up real estate. They also add another element of reliability that has to be factored into the system. But they're a necessary component, and especially in modular architecture. So we work very closely with the standards organization and industry leaders on making sure that our connector development supports the emerging architecture. So what I wanted to talk today about was the drive for functional density. We know what's happening in the embedded computing world with faster processors, more cores, higher I/O count. SWAP, we've been talking about for years, but we continue to drive size, weight, and power down to unprecedented levels and continue at that. The open systems architecture is very prevalent, and looking at modular scalable systems. So what does that mean in terms of the connector challenges? So from an interconnect standpoint, signal integrity plays a much more significant role than it has in the past. Going back a few years, the mechanical designers would develop a connector that meets the pin count and the space requirements. And then our signal integrity team would look at it, do some tuning, and then that would be the end product. Today, our signal integrity engineers are really defining to the mechanical guys what they need, what kind of structures they need to handle the next generation speeds. So as a mechanical engineer, I'm not sure I'm really comfortable with that, but the signal integrity guys have a lot of power in our organization on new connector development. There's more functionality within the connector modules themselves. We're working on some higher density contact solutions. So along a card edge, we could fit a lot more data and more capabilities. Lightweight materials and solutions are still important. And then we need to develop standard solutions for interconnect, but also have a capability to have flexibility in the application. So a lot of what we're doing, and when we developed VITA 67.3, which is the next RF interconnect module for VPX, we ran into this where we defined a standard interface, but allow some flexibility for the user to incorporate it into different platforms. So it's an interesting aspect to it. So really, it's all about how do you stuff 6U of interconnect into a 3U. Our engineers used the 10-pound, 5-pound with the S word equivalent to that, but it's the same thing. So we're just trying to pack more and more into a smaller space. So we can go back and look at the evolution of VPX and the data rates. The original VPX connector, the VITA 46 connector, was qualified in 2006. The VITA 46 specification was released in 2007. In 2010, OpenVPX was released. And then if you look at this note here from the frequently asked questions on OpenVPX from back in 2010, we're going to support 3.3 1/8 gigabit per second with plans to upgrade to 6 1/4. So today, VPX is being used at 10 gigabit per second applications. So that really has been a significant migration from just within the last 7 years. And if you look at the speed roadmaps, 3 of the major protocols, PCIe, InfiniBand, Ethernet, they're all looking at next generation speeds, and we're all developing systems around those data rates. So for us, as an interconnect group, we're looking at basically 2 levels of next generation products, looking at hitting that 16 gigabit per second window to handle the PCIe and InfiniBand FDR, and then also looking at beyond that, how do we get to 25 gigabits per second to handle 100 base KR4 applications. When we look at interconnect, and really focusing here on the interconnect between a VPX plug-in module and the backplane, it's not just the connector. So we can look at the connector, we can tune the connector, the PCB wafer construction within VITA 46. We'll optimize that. We'll look at all the transitions into the contacts. But then you got to start looking at the board terminations. You're looking at the traces on your backplane, on your plug-in, your carrier card. We got to look at the transition into a mezzanine card. So VITA 68, we're participating in that, providing connector models to that group. We're looking at the entire channel. So we're looking at the transmit to the receive, back through the backplane, that entire link. And that's really what we need to focus on. And VITA 68 is looking at all those elements and where that budget will be. So for higher data rates, if you have a 10 gig plug-in card or multiple 10 gig plug-in cards, they will be compliant with any 10 gig backplane. We need to make sure that that interoperability stays valid at those higher speeds. So one big factor and one of the big reasons that VPX is being used in 10 gig applications today is board design. There's a lot of elements in the board and that transition from the connector into the board structure. So board materials play an increasing role. Things like weave and even the copper roughness are more critical at higher speeds. We're getting into more complex via designs. So where standard through hole, there's back drilling is fairly common today to eliminate stubs in the board design in the board. But things like micro vias and dual diameter vias or more complex via structures that really help in signal integrity. Anti-pad layout. So as we lay out how those pairs come off of the through holes, the anti-pad size, nubbin designs are becoming more common. We're getting into some geometries that are non-symmetrical that allow us to balance skew coming out of the pair. And then trace routing is also obviously very important to keep that spacing between the anti-pad and how that trace may jog over to optimize it to get the traces out of the connector pin field. So we're very involved in a lot of the the industry leaders within this group to work on board designs and how we effectively design a connector that will transition into the board effectively. There's also a large growing interest in integrating RF and optics. So we do have within VITA, we have VITA 66 for optical modules and VITA 67 for RF modules. We're seeing more integration into slot profiles of those interconnects. So if you look at this view, this is an ELMA backplane that was developed and really is testing new platforms and new configurations at high speed. Off to the right, you'll see a module with 12 coax contacts on it. And this is a 3U backplane. So you basically got 3 inches between the guide pins where you have room for connectivity. Those 12 coax contacts are taking more than half of that real estate. So that becomes very significant in terms of how much density you have within a slot. You can also see there's a module there with open cavities of 10 cavities. That is part of what we've been doing on VITA 67.3. So we've been working on modules that are wider, that'll support a 1-inch pitch instead of a 0.8-inch pitch, which really is a large percent of the applications. And that allows us to get 10 coax contacts within a full module space. So a little bit of an increase in density and some new capabilities there by stretching out the size of the module. But what I wanted to focus on for this was the module that's shown there with the RF and the optics in it. So today, there's a slot profile for that. And this is what it would look like from an interconnect standpoint. Along a 3, you've got a P0 for the utility plane, which is the VITA 46 connector, half module. You've got a full module in the P1, J1 position with 32 differential pairs. And running it, you can run to 10 gigabit per second today. There's a VITA 67.1 half module. So it's 4 RF coax contacts. They're SMPM, rated at 26.5 gigabits per second, or gigahertz. And then you've got a 66.4 optical module with a single MT ferrule in it. So you can get 12 or 24 if you do dual row fibers within that. Next generation will be a higher density coax module. So here we're doubling the density to 8 contacts within a half space, running a higher frequency contacts to 60 gigahertz. We have capability also now to do direct attach to the plug-in card. So we could edge launch off the carrier card. We don't have to. You don't need to use cabling within a plug-in module, which also saves additional real estate. And this is really just a view, just showing a 0.8-inch pitch application. With a 1-inch pitch, we can get 12 contacts in. So you remember that view that we're taking 12 contacts, using up more than half the real estate. We can do that in half a module. For the optical module, we can double the density by resizing the guide pins, repositioning the MTs. We can get 2 MTs within a half module space. Again, so we're doubling the density and not taking up any more space on the 3U card. And the VPX connector itself. So we talked about some of the roadmaps getting to 16 gigabit per second. We've got designs there now. We're starting to tool initial testable prototypes that through the wafer development and through some board termination, we're able to achieve 16 gigabit per second. So that will be coming very soon. And then the next tier, 25 gig. So I think Jerry and Jing and others had corralled us and said, we really need to get to a 25 gig per lane data rates with the existing connector, make it intermatable. That poses some significant challenges, but we've got development work in process right now to make that happen. So really, if you look at a 3U card, we're more than doubling the density of the RF. We're doubling the density of the optics. We're increasing speeds a couple generations on the VPX connector, really driving for next generation solutions. And if you imagine what those can do when they're scaled out to a 6U, the incredible amount of bandwidth and capabilities you would have. So really a summary message, data rates are increasing, functionality is increasing, physical size and weight at a premium. And there's a really tremendous opportunity from an interconnect standpoint to align our roadmap with where the market's going. And you may not love connectors in the end, but we're going to make sure it's not the roadblock.